Now, another thing, we have to differentiate between D and E. The D is not only to scaled up with E, because E is due to everything, while E is due to everything what we have, like charges, whether the polarization charges are the actual charges, while D is something which is having some limitations. So we will have to differentiate between the two things. Like we wrote the Gauss's law for D as well, and is E we have written the Gauss's law like closed surface integral in E dot dA is equal to Q enclosed over epsilon naught. This we have written for E, the Gauss's law, and this is for this. So if symmetry means there will be symmetry, we can apply the Gauss's law for free charges as well. But can we say that D is just only a scaled up E? So it is not right. Because if, for example, I take this relation D epsilon naught E plus P, then if I take the gradient or the curl of this del cross D, then this is epsilon naught and del cross P, del cross E, and plus del cross P. Now I know here that if del cross E, we know for electrostatics, we know electrostatics, del cross E is always equal to 0 in case of electrostatics. We are in that regime. But if this goes to 0, then del cross D is not necessarily 0, because del cross D is non-zero, as we are having this thing del cross P, it will stay there. So del cross D is having the contribution from that polarization, and this is not supposed to be 0 always. So we have that del cross D is non-zero, is this thing is non-zero. So there is a difference, means material is there, and we have to keep this thing in mind. We are not to be deceived by this. That's why Griffith has introduced another section, a deceptive parallel. And another thing we can have here in this deceptive parallel, let me write that one as well. That is, we have written the means we cannot like E, we are having the Coulomb's law. The Coulomb's law means for the force, and from that we can directly write E. We cannot write D in this situation, because D of R like means it is not like the D is equal to 1 over 4 pi 1 over 4 pi and rho f rho d tau over r square, like this. And our unit vector here, this is prime coordinate, so I will write with the rho. If I write r with this one, so it will also be a prime coordinate. So this thing cannot be equal to this thing, is we are having for E. So all the things we are having for E is not the same for D as well. So these things are to be taken in count, that basically the electric displacement It helps us in calculating the field inside and outside of a dielectric material, but the electric field cannot be calculated inside a dielectric material. It can only be calculated outside of the material, and we can do this thing. The other thing is the boundary conditions are basically different. Like we are having as we have not yet done the boundary conditions, so it's better we these boundary conditions will come in the seventh chapter as well, and then in the ninth chapter as well. So we will try to do those boundary conditions in chapter 9. So here they are means the boundary conditions are also different for D and for E as well. So it is not to be confused with the D is just a scaled up E. Both are different from each other from different aspects, from the symmetry aspects, from the calculation aspects, from the mathematical aspects. They are different. So this is all for the electric displacement. We have written the electric displacement, the Gauss's law for dielectric in the presence of dielectric. Okay, we can solve an example on this, the Gauss's law for dielectrics. This is example 4.4, and let me read the statement of this example. The example is saying a long wire carrying uniform line charge lambda is surrounded by rubber insulation out to a radius A. Means that wire has been surrounded by a rubber insulation which is of radius A. Find the electric displacement. So we are supposed to find out the electric displacement. We are having a wire, and on that wire line charge density lambda is there. Lambda is the charge per unit length, and it is surrounded by an insulation, and the insulation is like this, and the insulation is of radius A. This is the insulation around this, and it is of radius A. And now we are supposed to find out the field. This is the insulation, the rubber insulation. So we are supposed to find out the field. We are supposed to find out the electric displacement, the field inside this insulation. So let's say we are going to find out in the field at a distance s from this wire. So we will consider the symmetry. The Gaussian means it will have a cylindrical, it is a wire, so it will have a cylindrical symmetry as we have done earlier. So this is like we are considering a cylinder around this wire inside this insulation material, and this is of radius s. This is of radius s, and it will have a certain length. Let's say consider this length is L. This is the length of the shape that we considered here for calculation of Gauss's law. Then let me write to calculate D here. We have that surface integral, this a closed surface integral, and the surface integral here S, and the D dot dA equal to the total free charge enclosed. So I have to write, means is d will be constant all over this shape, so it will be just d times area, d times the area of this, the cross sectional area of this. So the cross sectional area will be 2 pi SL, the cylinder area 2 pi SL, and this will be equal to the free charge enclosed. So the free charge enclosed will be enclosed by this cylinder, means the Gaussian surface that we have considered will be lambda times L. This will be the total charge. So I can write that D is equal to lambda L over 2 pi SL, and L will cancel. So I can write that D is equal to lambda over 2 pi S. And if I want to write it in a vector form, then D here and S, so it will be an S unit vector. So lambda by 2s is basically the uh, electric displacement inside that insulation. And now if I want to calculate the, this is inside the insulation. Now outside of this insulation, if I want to calculate the electric field, then outside the insulation I know that D equals epsilon naught E plus P, and outside the insulation P is equal to 0. So this implies that D is equal to epsilon naught E, and I can write that E will be equal to 1 over epsilon naught times D, and this implies that E comes out to be equal to lambda over 2 pi epsilon naught S and S unit vector. So it will be for when, for S greater than A, when this S will go out of this insulation, out of this material. So this way we can have the electric field outside of the material. We cannot calculate the electric field inside the material because we don't know the value of P there, that what will be the value of P. So this way we can calculate easily, and this we have done already, that electric field of such a geometry will come out to be this.